Good morning, General Chemistry 2. How are you today? I'm going to have to keep my videos just a little bit shorter. So this is going to be a whole series of videos. We are on the second half of our kinetics unit. This is unit 2. We're going to do kinetics. And we are going to focus on something called the integrated rate law. And with our integrated rate law, we're actually going to have probably 4 to 5 videos for this one. I'm going to keep this first video nice and short, but what I want to do is define the integrated rate law and give you an idea of why do we need another rate law? What are we looking at? Why do we even need that? And then what are we going to do with it? So let's define everything in this video. Let's work our way through what it is and why we need it. And then we'll switch and we'll do another video for each type of integrated rate law example. So this one is definitely the first video in this series. You want to watch this one first. And this video, we're going to kind of define everything. So let's take a look. What have we learned so far? The journey so far. What have we done in our kinetics? Well, the first thing we looked at, we called the general rate expression. We took a look at our equation and we got a nice general picture of what we're even looking at in our reaction and in our kinetics. And we put together a perspective of that reaction. So we are watching our reactants disappear over time. And then we're watching our products appear over time. But when we looked at the data for this, we really just had a couple of data points, and what we ended up looking at was a nice average rate. So it really just got our feet wet. It gave us perspective. What are we looking at in our equation? What are we trying to solve for? We noted that if we saw a data set that had concentration versus time, that was our general rate expression. I'm going to add to that what if we have just a couple data points? That is what we're looking at. Just a general idea of what's happening in our rate. And we're calculating an average rate. But then we started to realize, well, wait a second. Isn't concentration one of our factors that affect rate? So we got a little bit deeper and said, okay, well, our general rate expression is still valid, but the actual data points we looked at didn't give us a real picture of that reaction because our concentration is going to be changing over time. Well, our concentration affects our rate. So then we moved on to our rate law and we started to learn even more about our reaction, and we wanted to connect now the how. So we studied, all right, what happens when that concentration changes? What is happening to our rate? And then what does that mean in our equation? So we started to get a little bit of a better picture of how our reaction is happening. And we solved for 2 really key points in that rate law. The first one were these exponents. Remember, those are not moles. That is the order of our reaction. That is key. That order of the reaction is giving us the how. So if we had a 0 order reaction, remember it wasn't present in our rate law. What if we had a first order reaction? Well, that substance was definitely having an effect on rate with concentration, and it was something that was likely decomposing. What if it was second order? Well, now we've got 2 things colliding, and that concentration does affect the rate. So it's really, we had to solve for that. We had to literally solve for order of reaction. And the order of a reaction is one of the key pieces of information you get from kinetics. And you cannot guess it. You cannot wing it. There's no way to predict it. That is all up to Mother Nature. You have to solve for the order of your reaction. And then after we had the order of our reaction, we got to solve for the rate constant. So now we're getting somewhere. We're getting a nice picture of that reaction and how things are happening in that rate determining step, which is pretty cool. And now what if we wanted to get even more information? So we don't want to let go of this idea of concentration versus time. What we want to do is include, wouldn't it be perfect if we could do two things? All right, let's talk about what those two things are. What if we could combine better data? So remember that general rate expression with only 2 or 3 points of data. If you know that your reaction rate is changing with concentration, 2 or 3 pieces of data really doesn't give you a whole picture of that reaction. So what if we could get better data? And then number 2, what if we could combine the rate law? So in other words, what if we could take into account the how and get better data? What if we could do both of those? Now we could get a much more, oh, this is not an English class, true picture of what is going to happen in a reaction. So if we wanted to ask probably one of the most common kinetics question, what would be a concentration at any given time? And we're taking into account the rate law. Well, sweet Jesus, now you're talking turkey. Now you're getting really good information from your kinetics. In fact, so good, I have to say that again. Wouldn't it be awesome? Our ultimate goal for most of kinetics is to ask a simple question. What would be the concentration of one of your species at any given time? And have it take into account the rate law and have a pretty accurate picture. So let's say something, we mentioned this in the other video, you're taking an ibuprofen and you're wondering, well, wait a second, why do I take one every 4 hours? Why not every 8 hours? So how much is left in your system after 3.5 hours? All of these are kinetics experiments, and all of these would come from good kinetics data to figure that out. So how do we combine them? Well, it's actually going to require a little bit of calculus. Now, calculus is not a prereq for this class, so don't panic. I'm going to give you the answer. But if you've had some calculus, I am going to give you some hints and then let you pause this video before the answer and see if you can integrate and get to the actual integrated rate laws. It would be pretty fun. Okay, so the first thing we're going to do is notice that both the general rate expression and our rate law, they both equal the same rate. So why can't we set them equal to each other? We totally can. And now if we can look at this as a math expression, which it is, and keep in mind our general question that we want to be able to find the best data and solve for concentration at any time, we're going to use a little bit of calculus to do that. So the first thing we're going to do is look at both sides. We're going to do something called integrate with limits. So if you've had some calculus where you can integrate with limits, that's what this is. Okay, we are going to start at, if our goal is concentration at any given time, well, in our reaction, you notice in our rate law, we have only reactants. So we're going to include only that reactant part. At any given time, let's start at 0 because we know that at 0 time, what those reactant concentrations are. You're in the lab and you're in charge. Is it 1 molar? Is it 5 molar? Is it 3 grams? You're starting with that concentration at 0. So we always know that. So our limits are going to be from time 0 to any time after that. So we are going to integrate with limits between 0 or initial and any time t. Okay, I love it. Okay, now I want to give a hint. And what we're looking at then, remember our second thing. So our first thing is we just combined our rate law and our general rate expression. Awesome. But remember our second thing was that we need better data. So why do we use calculus in here? Why are we looking for derivatives and why are we integrating? Because what's happening is that this is going to let us have infinitesimal changes. So we're literally going to have, in theory, an infinity number of data points. This is awesome. So if we want better data, this is the best way to get it. Okay, we're going to literally have infinitesimal changes in our data. So let me write that down. So if you can have really tiny changes in your data, and then you can get towards an infinity number of data points, that's really as good as it gets. And that is what this expression is going to let us do. So let me give my calculus people a hint, and then go ahead and pause if you want to derive. Anytime you see that change, because that's our point, right? We want much better data from this. We want that change to be phenomenally teeny. So anytime you see that change in our expression up here, you are going to do that, okay? And then the second thing I want to let us know is that if you've had your math, again, you don't need to, I'm about to give you the answer, but if you've had your calculus, you know that depending on what your order is, you are actually going to get different solutions. What? All right, so let's pause for a second. So my calculus people, pause this video if you want to have some fun and go ahead and try that integration and see what you get. For those of us who haven't had calculus recently, or if you haven't had calculus at all, I'm going to go ahead and give us the solutions. So the first thing I want us to focus on is the fact that your order is going to give different solutions. If you want to think of it this way, you are doing math up here. And certainly your math is going to be different if that exponent is 0, 1, 2, 3, 4. So the first thing we're going to notice is that we're actually going to have a series of equations. And those series of equations are going to be based on order. So we're going to have to organize your cheat sheet a little bit into the different orders. Now, in this class, we're going to keep it extremely nice and straightforward. We will deal with 0 order, first order, and second order only for our integrated rate law. And that's pretty traditional. If you're looking up integrated rate law, that's what you're going to find. Okay. And then I hope you're getting a picture here that if we're looking at super small changes in our data points and we're getting to a place of infinity number of data points, we're going to likely be plotting. So when we plot our solutions, so when we plot that series of equations, so when we plot that equation, we're going to find that it is linear with the correct order. Okay, that's awesome. That's going to be a clue because it means we can solve for that order in 3 different ways. This is perfect. So let me spell out where we're headed to next. All right, let me give the actual equations for each one of our orders. And I want to give you an idea. Why don't I go ahead and write it up here? We're going to look for the order of each reaction. Order is going to be huge. We're going to have 3 ways. Okay, we saw the first way. Can't we solve our rate law? That gave us orders. So if you have that set of data, you can calculate your order. Number 2, we're going to plot our data. And we're going to look for the one that's linear. That is going to spot our order, because if our linear gives us the correct order. And then number 3, you may have the occasional crafty worded problem that gives you the unit to K. Our unit for K will also vary by order. Now, do you notice in our videos beforehand, we have conveniently skipped the units to K. This is why it is the third solution. So if you've got a sneaky problem and you already have solved for your rate constant, the units on your rate constant vary per order. So all of these are connected to the order of the reaction. So let's make one big cheat sheet for you. And I'm going to stop this video and then we're going to go through the orders because I've had a difficult time saving these. So let's look for part B, and I'm going to give you all the equations for 0, 1st, and 2nd orders. Okay, see you.